So far in chapters 7 and 8, you've learned how to manipulate energy balances, how to define reference states, and how to calculate the changes in internal energy and enthalpy from their heat capacity values, or heat capacity functions. What we're going to do now is we're going to combine all these concepts, and what I want to do for you is define a general strategy for solving these energy balance problems. Now, for the first step in solving an energy balance problem, it's actually not to deal with the energy balance first, is to actually just first perform all the required material balances. Because these molar or mass amounts or flow rates in these material balances, those are the same ones that are going to show up in your energy balance. And so in order to solve your energy balance, you need to know these mass or molar amounts. So that's what your first step should be, is to at least define all the equations in your material balances. The second step is now you could start going to the energy balance. And here you want to write out the appropriate form of the energy balance, so determine whether you're dealing with an open or a closed system, and then delete any terms that are negligible, things that are insignificant in your system. Once you write out your simplified form of the energy balance, you should then choose a reference state for your system. And so what that requires is for you to pick a phase, temperature, and pressure. And so you're going to choose a reference state. Let me write the word state here. You're going to choose a reference state not just for one species in your problem, but you're going to do this for every species that are involved in the processor system. And what I want to emphasize here is that you don't need to use the same reference state for each of the species in the system. In fact, every species that's independent of one another can have their own reference state. Own unique ref state. Another piece of advice is, if you're looking up specific internal energies or specific enthalpies in a table, it makes your life a lot easier if you just, for that species, use the reference state of that table. Okay, so by tables I mean, for example, the steam tables. But if you're not looking up the internal energy or the enthalpy values in a table, my other recommendation is to choose the inlet or outlet conditions of that species, so that, let me write this first. Choose one of the inlet or outlet conditions as the ref state for the species. And the reason for doing this is because if you set either your inlet or outlet stream as a reference condition, that means that you could set your internal energy or your enthalpy values to 0 in that stream. And so that will make your calculations much more simpler if one of the terms is just equal to 0. In any case, after you define what your reference states are going to be, you should then construct what I'll call an internal energy or enthalpy table. And so we'll see an example of this in the following video. But basically what these tables are good for is they help you keep track of all of the U or H values in your problem. Because these energy balance problems can get quite complicated. Throughout the process. And once again, you'll see examples of this in the following video and of course in class as well. Examples later. Alright. Then, once you set up that table, what you should then do is then calculate your U or H values for each species and at the inlets and outlets, right? And then insert them into the table. And once you have the specific U's and H's, then you could actually calculate the extensive versions of U and H. So delta U or delta H. Right? And so to calculate these U's and H's, right, that's typically going to involve taking an integral of their heat capacity data. Right? And then finally, once you calculate those U's and H's, calculate any other terms in the energy balance that are left or that are not negligible. Right. And of course, solve for any unknowns. And a lot of times, especially since we're dealing with engineering, we're concerned about estimating, heats or work terms. And so typically, that's what your unknowns are going to be. All right, and so here's just the general outline for solving these energy balance equations. And now we're going to focus on actually applying this approach in order to solve these problems.